All right. Hello, all. This is section 5.3. It shouldn't be too long. It's about 9 slides, so it shouldn't be too long. And again, you need to watch this before class on Monday. So let's get started. All right, so we're talking about this section, talks about diagonalization. And so we're going to be talking about diagonal matrices. And so just remember, I'm not going to write this down, but just remember that a diagonal matrix is a square n by n matrix whose non-diagonal entries are zero. So the only non-zero entries are along the diagonal. Everywhere else in the matrix and the square matrix is zero. And you can see page 94 in your book for that definition. Okay. And so it's nice to work with diagonal matrices because they have some nice properties that just makes it easier to compute matrices and do different things with matrices. And so that's what we're gonna be talking about. All right, so here we have some nice properties. So it does not mix components of x, of vector x in the product dx. So consider this 2 by 2 diagonal matrix here and some vector x here. And if you do matrix vector multiplication, then we see that the x1 component stays with the top entry. The A. Okay, I'm sorry. The A entry, so the scalar stays at the top and B stays there. So they don't mix. So, sometimes we can multiply if we're talking about in general A, B, C, D, and we can get A plus B or C plus D. Okay, so that's what this first thing is saying, is they don't mix components. And if we take a higher, so it does not mix components of proper size of A in the product dA. So not only does it not mix with vector matrix multiplication, but also with matrix multiplication if you have a diagonal matrix. As we do there, that 2 by 2 matrix times this 2 by 3 matrix, then you see that the A's stay in the top entry and the B's stay in the bottom entries. Okay, and it's not mixed. All right, so that's a nice property we have. We also know that if we have to find higher, if we have a diagonal matrix and we have to find higher dimensions, or if we raise it to some power, it's also nice to compute that. It's easy to find. And so I just gave sort of 3 examples, one with actual numbers. So if we have that diagonal matrix there and we square it, we see that it gives us, to emphasize the point, I wrote it as 2 squared and 2 squared, which is, we know, 4040. But if we had in general diagonal matrix A0, 0B and squared it, then our outcome will be A squared, B squared. And so if we have something cubed, right, in the diagonal matrix, then when we look, I guess, okay, you guys can see it now. It's A cubed, B cubed, and that's a nice thing to know, right? So in general, then, that means we can say if we have a square matrix A0, 0B raised to some K power, then looking at what we just, those few examples, we can say that's going to equal A to the K 0 and 0B to the K. So you don't have to, if it was, if it was raised to, say, the 10th power, then you don't have to, string out 10 matrices and multiply them, right? You can just, if it's a diagonal matrix, you can just take the components and raise it what we did there. So that's a nice property that we have with diagonal matrices. So in fact, it would help us if we could somehow use that to our advantage and maybe solving for general matrices and things of that nature. So let's look. Okay, so first, let me give you this definition, and you may have to pause the video and write this down and really make sure you understand what's going on here. So we're saying if we let P be an invertible matrix, right, and we know that means it has an inverse, and D is a diagonal matrix, then we say A. Now, A is any square matrix, right? It doesn't have to be diagonal. We're saying that A is diagonalizable. Okay, that's a big word. If A is similar to D. And when we say similar, we mean that A equals P times D times P inverse, or D can equal P inverse times A times P, or A times P equals P times D, okay? Now, this one here I just sort of gave to you. Basically, to do that one, you would need AP. So this one is helpful if you know AP and D, but don't know P inverse, right? Or if it's not as easy to find P inverse. So if you have AP and D, then it's easy to use this one to show that A is similar. If not, we may, for the most part, use those two in terms of A and D in terms of that one variable, okay? All right. So if one of these cases exists, we said, oh no, don't do that. Okay, I'm just coming back from my trip, so yes, we say, not sad. We say that A is diagonalizable or A can be diagonalized, okay? And I just wanted to show you how, I could have showed you for all three, but I just wanted to show you how these two here are equivalent. And so that's what we have over here. So let's say we start off with A equals P times D times P inverse. Then remember too, when you're multiplying matrices, that it's not commutative, right? So matrix A, you don't have to write this down, but matrix AB is not the same, or it doesn't necessarily have to be the same as B times A, right? So we have to be very careful when we're doing matrix multiplication, because the side that we multiply on is very important. Unless you know the matrices are commutative, which you don't unless it's given to you, right? So here we don't know if it's commutative, so we have to be careful. So by taking this, the first thing we do is multiply both sides on the right by P. And that's what I did here. So I just took P and multiplied it by both sides on the right of that equation there. And that gave us AP, which is equal to P times D times, and I put this in parentheses, P inverse times P. Well, we know right here, this is the identity matrix. So that's the same as saying that we're multiplying a number by 1, right? Which doesn't change anything, right? So that's just a 1, or that's just becomes our identity matrix. And so that leaves us with A times P equals P times D. So we actually just showed that one right there. Okay, cool. Now, but I want to show this one. So now we take P inverse and multiply on the left, okay, of the matrix or of the equation. So that becomes P inverse AP equals P inverse times P, and I put those in parentheses times D. And so again, that's the identity matrix. And so P inverse times A times P equals D. Okay, so all three of those statements are equivalent. And if you can show one of those statements exists or is true, the equation is true, then that tells us that A is can be diagonalized or A is diagonalizable. Okay. All right. So now that we know that fact, if we know that A is diagonalizable, then we can use that fact to help us find higher powers of A. All right, now it becomes easy to commute. So again, if we know that A is diagonalizable, then A equals P times D times P inverse, right? So then if we look at A squared, which is A times A, using substitution, that's P times D times P inverse times P times D times P inverse. And we see we have the associate property, so we can put those two together, and that becomes identity matrix, which leaves us with P times D times D times P inverse. Well, D times D is just D squared, and so we have P times D squared P inverse. All right, and again, that's when we took A squared. Well, what if we cubed A? Well, A cubed is the same as A squared times A, and I broke it up like that because we know we can replace A squared with that value, and then we already know what A is, right? So this becomes P times D squared times P inverse times P times D times P inverse. And again, we can put those two together, and that becomes identity matrix. And so we have P times D squared times D times P inverse. It's a lot going on here, but this becomes P times D cubed times P inverse. So then we can make, from those two examples, hopefully you can see the pattern for our general expression. So when we have A and we know A is diagonalizable, then we can say A to the K equals P times D to the K times P inverse. Okay, which again is very nice, something that we can do to make it easier to compute our matrices of higher powers, okay? So keep that in mind. All right, only a few more things, which is kind of the heart of, we're going to get into the heart of what's going on. All right, so let's say we're given some matrix A, right? We need matrices P and D such that, or that diagonalize A. Okay, so again, recall A is equal to P times D times P inverse, which is the same as D is equal to P inverse times A times P. Okay, show that A is diagonalizable with P equaling 1, 1, 0, 1. Okay, so now P is given to you in this example. It's given to you. Well, since it's a 2 by 2 matrix, we can easily find P inverse or determine if there is an inverse. I'm assuming there is an inverse because it said this is the P, right? But we can always check if you do the determinant of that matrix P, it'll be 1 minus 0, which we know is not equal to 0, so therefore it is invertible. And for 2 by 2 matrices, you guys remember that formula to find the determinant. And so our the inverse, not determinant, our inverse. So our inverse becomes 1, 1, negative 1, 0, 1. Okay, and so using this formula here, because in this formula we need P inverse A and P, right, which we now have. So this is our P inverse, this is our A, this is our P, and make sure you check on your own to confirm, and you can multiply, it's multiplication, so you can multiply with those two first, or if you wanted, you could take those two and multiply them first. It's up to you, right? Okay, but you should all receive the same answer. So just stop the video for a minute and quickly do this and confirm that you get that matrix, okay? Because I could have made a mistake, so confirm it. All right, so P and D diagonalize A, okay? Thus, A is diagonalizable, okay? And recall, too, that we did this to find D, right? Gave us D, and we needed to make sure. So notice that D is diagonalizable, right? Because actually, I could have done it the other way. The only non-zero entries, well, this way. This is the only non-zero entry, and it's along the diagonal. Okay. All right, so now you might be asking, well, what if P isn't given? How can I figure out what my P and my D is to show that A is diagonalizable? Great question. All right, so we have this nice theorem called the diagonalization theorem. And so it says this. So if we have A is an n by n matrix, excuse me, A is diagonalizable if and only if it has n linearly independent eigenvectors. And you all should know by now from the last couple of sections, how to find your eigenvectors, right? So if it has n linearly independent eigenvectors, A is diagonalizable. That's the if and only if proof. So that means if and only if, meaning it goes both ways, right? So if you know A is diagonalizable, that means it has n linearly independent eigenvectors. And if it has n linearly independent eigenvectors, then it's diagonalizable. Oh, say that in one breath. Okay, so if A is diagonalizable, we have something else. The columns of P are the eigenvectors of A, and the diagonal entries of D are the corresponding eigenvalues. Okay, so we have this connection between a diagonal matrix, or determining whether a matrix is diagonalizable, connected to our eigenvectors and our eigenvalues, okay? And theorem 6, now notice this is not an if and only if proof, so I want you to be careful. And in fact, your book has some nice examples, because you need to read the book, of course, and I know you all do. The book in this section has some nice examples to show that this is not a if and only if theorem. So this theorem 6 says, an n by n matrix with n distinct eigenvalues is diagonalizable. This is not if and only if, meaning if you have an n by n matrix and their eigenvalues are not distinct, then it's not diagonalizable. That's not what this is saying. This is saying if you have an n by n matrix with n distinct eigenvalues, then it is diagonalizable. Because you could have a multiplicity, an eigenvalue that has a multiplicity, but maybe when you find the eigenspace for that eigenvalue, it spans two eigenvectors. So let's say, and again, you don't have to write this down, but so let's say we have some matrix, a 3 by 3 matrix. And let's say the eigenvalues are -1 with multiplicity 2 and 2, right? So you might think, well, it's not in distinct eigenvalues, so it's not diagonalizable. But this is not saying that. This is saying if you do have the case, then it's definitely diagonalizable. Now, if you get this case where they're not distinct eigenvalues, then you have to do more work to determine whether or not it's diagonalizable. Because again, this could have a span where it contains 2 elements, and this is a span of 1, and therefore you have, if it's a 3 by 3 matrix, you have your P, right? The columns of P, which is the 3 by 3 matrix, and so it's diagonalizable. So I just want you to be careful. The book has an example of this, so make sure you read that. And I don't want to be too long because I'm trying not to go. I was trying to stay under 15 minutes, so just bear with me. A couple more minutes, and we'll be done. So here we have is A diagonalizable, all right? So the first thing you need to do, again, because we have this relationship between our eigenvalues and eigenvectors, is to figure out our eigenvalues. And we know how to do that. We take A minus lambda I, we find the determinant, get the characteristic equation, set it equal to 0, and we have our eigenvalues, right? Okay, so stop here and see if you can figure out the characteristic equation, because I skipped steps and here's our characteristic. Well, this is sort of the setup for our characteristic equation. The equation, we would have to multiply this through, right? So on that quiz, hopefully you're listening to this before you turn in that quiz tomorrow. If you stop here with your characteristic equation, I will mark off because you have to distribute all the way through if you're asked to find the characteristic equation. All right, you're welcome for me giving you that. Okay, so now the eigenvalues are 1, 7, -3. Therefore, now, so this is the case we can use theorem 6, right? Because we have an n by n matrix with 3 distinct eigenvalues, n distinct eigenvalues. Therefore, we can say by theorem 6 is diagonalizable, and we're done. Also, remember, D, the diagonal matrix, is composed of the eigenvectors. And so here's our diagonal matrix. Now, 1, 7, and 3 could be in different places along this diagonal. So I just wanted you to know that, okay? And P, the matrix P, will be vector 1, vector 2, vector 3, where V1, 2, and 3 are the eigenvectors of A. So you guys remember how you have to go back and put in each of these eigenvalues and reduce the matrix and find the span, the eigenspace, and there you find the eigenvectors. All right, we are done. I'm sorry I was trying to stay under 15 minutes, but you guys hopefully understand this. And of course, you'll be working on this tomorrow in class. Bye.